Hello and welcome to this session, Multi-Cloud High-Performance Engineering Simulations with Ranger. The agenda of this session is organized as follows. First, we start talking about multi-cloud challenges, specifically for engineering workload. Then we talk about HPC engineering workload stack on Kubernetes. Finally, talking more about UberCloud's HPC containers and the engineering simulation platform built on those HPC containers. Finally, we talk about how this platform is integrated into SUSE Rancher, the multi-cloud management platform of SUSE. Then we conclude with a customer use case, how this platform was used for running engineering simulations for repairing defect hard valves. About me, my name is Daniel Gruber. I'm Director of Architecture at UberCloud. Before, I had a long history in developing core components of Grid Engine at Sun Microsystems, Oracle, and Univer. Then I moved on to be a platform architect at Pivotal, and now, since 3 years, I'm committed to pave the way to HPC as a service by building with my colleagues a platform based on Kubernetes. You can reach me at the email address you can see here, or you can find some of my free time hobby projects on GitHub. So, what is UberCloud? UberCloud was founded in 2012 with a mission for helping enterprises to run engineering workload in the cloud. It's headquartered in Los Altos, in nice California. And at the very beginning, UberCloud started with a huge amount of community experiments in the early days of HPC in the cloud to learn what it means to run HPC workload in the cloud. Then, after Docker has been announced and released, we quickly adopted the container concept also for HPC workload. Finally, in the year 2019, we moved on to use more and more Kubernetes as an HPC platform backend. We are providing an on-demand, self-service cloud HPC platform running on different clouds like Azure, Google Cloud, AWS, as well as on private clouds of some of our largest customers. We are used by some of the largest tech companies around the world. We got more than 10 industry awards. Since 2015, we are Azure HPC partner. Since 2020, we are GCP Tech partner. And 2022, we are proud to be SUSE Gold partner. Let's start by looking into the multi-cloud challenges for engineering workload. There are two great reports. One is the Flexera State of the Cloud report, which is meanwhile available in the version 2022. They stated that 29% of the enterprises have a multi-cloud strategy and 28% have a hybrid cloud strategy. On average, they see that 2 or 3 clouds are used, and the biggest problem is the wasted cloud spend. The other great report is HashiCorp's survey. Both are linked in the slide. Here, 47% say that their problem is skills shortage on the cloud for their employees. The major driver for multi-cloud they see at digital transformation, avoiding cloud vendor lock-in, cost reduction, and scaling. For engineering HPC workload, it's slightly different. Our customers are telling us that they want to use a different cloud because applications perform better, or they want to achieve savings through cheaper, better tailored infrastructure choices, such as spot instances, or they want to have a workaround for the today very common out-of-stock problem or quota limitations. Finally, another reason we see is that IT just decided to use a different cloud additionally. So how does an HPC engineering workload stack on Kubernetes look like? In order to understand that a little bit better, we should look into how an enterprise workload differs from a typical HPC engineering workload. For an enterprise workload, you are dealing with microservices architectures. You have a lot of redundant instances in order to have a scalable application, but also a high available application. The containers are small to provide a high density, even higher density than on the VMs. So you have many containers on a single node, and they are communicating through a message bus like Kafka or PubSub or RabbitMQ or Redis. They are typically distributed across different availability zones or even regions to provide high availability. They are highly secured through a networking, through usage of overlay networking and things like Istio. Typically, they are providing a service to an end customer which runs endlessly. That's different to HPC engineering workload, where you have a single application distributed across multiple nodes. You have huge containers sometimes, since the application footprint is large. So we are seeing applications which are dozens of gigabytes in size. A single application can fill a complete cluster. There is no node sharing required. Communication happens through an MPI standard. The nodes should be located near each other in order to have low latency communication, which is crucial for the performance. But also the data should be stored near the nodes. Typically, a shared file system is going to be used or a parallel file system. Passwordless SSH needs to be configured so that an MPI application communicates or works perfectly. An overlay network does not really work because of this huge performance impact. Typically, an engineering HPC workload has a defined end state, so it's more like a batch job. HPC workload depends on specialized cloud features, but also on-premises, it requires these features. So you need to have a network latency, which is very, very low, network bandwidth, which is high, fast storage is crucial, high memory machines are required, optimized CPUs with large caches and high core count are preferred in order to have the application on as less as possible amount of nodes while giving you a good performance. It is required to have optimized OS settings like turning network polling on. HPC workload can use GPUs for speeding up computation. And HPC workload also requires often a license server in order to use existing shared licenses from a pool. If you're looking how an HPC cluster on premises look like, you can see something very similar to this diagram here. Often you have multiple login nodes where the engineers are logging in and submitting their workloads, their simulation, to a centralized workload manager, which is aware of all these compute nodes distributed across the cluster. There is an accounting and reporting interface, which sometimes is connected back to the workload manager so that the workload manager can drive its decisions based on past workload usage. There is a shared common file system available on all compute nodes. The sizes are very different, so they range from tens to thousands of nodes. You have a sharing of the hardware across users, across different projects, and even departments. The resources are sometimes very inhomogeneous, meaning you can have nodes with GPUs, you can have nodes even with tape drives attached, you can have nodes with other accelerators. the focus here is really on having an efficient usage of the resources. And in order to have that, job queuing is crucial. So typically on a Friday afternoon, engineers submit their workload so that they have the results available on the Monday morning. So then the job queue is packed, and over the weekend, the workload is getting processed one after the other. HPC in the cloud is very different. There you have on-demand allocation of resources. So you can have a pay-per-use model. There is no node and resource sharing required for users, projects, or departments. So there is less job queuing required. Still, you have some limited resources like licenses, where job queuing can be useful, or in a high job throughput scenario. You have a central VM scheduler, but this is coming from the cloud provider, which you don't have really external access to. You're just requesting your resources and then you get them, which you can use immediately or not at all. For monitoring, accounting, and reporting, typically the cloud platform provides everything you need. Or when you are using multiple clouds, then you can use a multi-cloud platform like SUSE Rancher. So in total, there are less properties of a standard HPC workload manager required. So replicating a shared on-premises cluster in the cloud one-to-one is very questionable. We have two types of workloads. We have a remote desktop where an engineer can log in and work with its application just like he does or she does on its desktop. This desktop can run hours or even weeks. There are GPUs required for getting a good performance for the remote visualization. It's an interactive usage. You do pre-processing there, you do post-processing. You can do workload monitoring or even do file staging from there, from your desktop to your remote desktop. Simulation runs are different. They run a very long time, sometimes hours to days. They have a defined end. Typically, what we see in the enterprise, which is different to research, is that we see up to 10 large machines being used per simulation, per application. It is always a licensed software. You have interactive pre and post processing driven from the desktop. Often there is a high CPU network latency, high CPU requirement, and the network latency needs to be very, very low, and the I/O requirements are crucial to get a good performance for the simulation run. And typically you have you have large input and output files of the simulation, which then opens questions about which kind of storage to use. So what are the challenges for Kubernetes in the HPC world? So Kubernetes expects containerized workload. Okay, in the enterprise, this is not a topic. But for HPC, then it is different. The HPC community worked on its own solutions since many, many years. They came up with their own workload, with their own solutions like Singularity, which is now Uptainer, Shift, and Charlie Cloud. The key here was that they wanted to support an existing HPC workload manager with the new container capabilities, which didn't work very well for the Docker concept. So Kubernetes also lacks on a native MPI support or on a concept to simultaneously start pods on different nodes so that they form an MPI application. It's more written for dynamic environments where you have a lot of operators which are updating, which are looking at the desired state and looking what the current state is and driving the current state to the desired state. There is not so much going on in fast shared storage integration, like using BGFS, and also for fast host networking, like Infiniband. This is getting started right now, which is very helpful for our workload. For remote desktop access, we require GPUs. This is often very well supported in Kubernetes, but challenges here are things like we need 32-bit libraries for specific software, which does not come with a standard GPU driver installer. In order to get this application into a Kubernetes cluster, you need this container. So UberCloud has a practice in about 7 years or 8 years writing such containers, which are Docker compatible, OCI compatible, and packaging commercial HPC engineering tools like ANSYS, COMSOL, StarCCM, and so on. They also bring the capabilities to have a remote desktop inside the container. So when it is started on Kubernetes, you can log into the container and work on a desktop-like environment. We have GPU support, we have MPI support, we have high throughput and low latency network support by using host networking on Kubernetes and having the necessary Infiniband drivers available as daemon sets. We have a built-in HPC workload manager like Slurm into our containers, which can run on multiple nodes in order to provide the application, which also runs in the container, a familiar interface to submit engineering simulations. There is batch job support. We have self-service capabilities for the engineer so that the engineer, during his work with the application, can resize the cluster to his needs. There is no queuing required, no waiting. The engineer has a dedicated set of resources. And of course, we are supporting spot instances or preemptible instances, which saves us a lot of costs. In total, we have packaged many more than 100 different applications into containers. So, for example, ANSYS, they provide a huge amount of tools like CFD, Mechanical, LS-Dyna, Numerical, and so on. We have NumMaker, Siemens StarCCM, Simulia, COMSOL, and all the tools from the EDA providers like Synopsys, Cadence, or Mentor Graphics. So how does UberCloud's engineering simulation platform on Kubernetes look like from a very high-level point of view? First, we provide a self-service user interface for an HPC engineer, which has a simple selection for the application he wants to use. After the user presses a button, a new Kubernetes cluster, fully configured with UberCloud's containers, is started. Once the containers are up and running, the user gets a welcome email with the concrete login details to the remote cloud desktop. Then he can work in the cloud desktop like he is used to work on his own desktop, but has a more flexible, more capable cluster behind. When the user wants to run simulations, he can simply resize the cluster, which is exclusively allocated for this particular user and this particular application. Once the user is finished to work with the applications, he can simply shut down the complete infrastructure, even not being aware that he was using a container or Kubernetes in the background. But IT has the advantages that all these Kubernetes clusters can be registered as a central Rancher installation for monitoring and debugging. If the user or the customer just wants to use one single cloud provider, he can also use the cloud provider's means for maintaining Kubernetes clusters. For integrating or providing customers with a flexible way to integrate that into their system, we provide a container as well as a command line tool which can allocate Kubernetes clusters. Those container or command line tool can be integrated in any existing HPC cluster, any CI/CD pipeline or DevOps pipeline, or any workflow engine. So how does our multi-cloud Rancher integration platform integration look like? There are two ways for integrating into Rancher. The first way is creating an AKS cluster, GKE or EKS cluster, and importing that in an existing Rancher installation. The other way is that our tool can allocate an RKE cluster independent of the cloud provider through the Rancher API. But we have special requirements. On Azure, for example, Infiniband is the fastest network option. Infiniband offers here 200 gigabits per second throughput and a latency as low as 2 microseconds between two containers. But that requires special machine types. So how to use that in Kubernetes? First, you have to select the right machine type, install the Infiniband driver on the host, and configure the devices. Then you have to install a compatible userland stack into the containerized application like libfabric. Finally, you have to configure host networking for the container in order to get access to the Infiniband device, and passwordless SSH, which should not conflict with the SSH running on the host. For AKS, we need a new feature called single placement group. This single placement group is very new and it was available only for VMs in the past. So for RKE, it was never a problem to have Infiniband on Azure. But for AKS, this is now a new feature. Be aware that there are no drivers yet pre-installed. Maybe this comes over time. And there are kernel changes every week to the underlying host OS. For installing the Infiniband driver, we created a daemon set. The daemon set contained the Mellanox driver and a precompiled version for this particular kernel. Then we mounted a root file system of the host into the container. Then we did a change root into the mounted root file system and run the installer so that it is executed on the host. Finally, we need to set up the device and finalize the host configuration. And then allow the applications to run containers on that particular host. For RKE, it's slightly different. RKE allows us to select the host OS. So when using SLES, it is very easy since there is a single zipper call, RDMA core, which allows us to install the driver. For more details, you can find here on the right side. When you're using CentOS, you have to install everything from scratch and compile the driver. This takes a long time, up to 7 minutes for us. When running HPC applications like the LS-DYNA car-to-car benchmark, which is very well known and available in different resolutions, on RKE, we looked at the impact of the host OS. Does the host OS has some impact on the performance? So we compared SLES 15 SP3 to very well known or very often used HPC operating system CentOS 7.9. And we found that SLES is in this context slightly better, but consistently better than this CentOS version. The other interesting thing for us was how much influence has a Rancher import, so when we are using an AKS cluster versus an AKS cluster which gets imported into Rancher, how much influence does this have for HPC workload? So we figured out that if we are not overloading the cores, the impact was very, very little. So as you can see here, the run times in seconds, so AKS without rangers was, the LS Dyna was running in 7,603 seconds, and with Ranger, it was just 50 seconds, a little bit more than 50 seconds more. So it is not any impact. But when over-allocating the node with more processes than available as cores, there is indeed an impact of a Ranger import, because you have more daemons running on the host, which cause the worker processes of the LS-DYNA application to jump between cores or even NUMA nodes, which invalidates caches and causes memory migration. This is a common phenomena in HPC. So our learnings and recommendations on that part is that we have to strictly avoid process and CPU overallocation. The performance impact of Ranger import is minor compared to the advantages of what we have with Ranger for monitoring and debugging. RKE has more processes running on the host compared to AKS or GKE. So it is not as lean as those Kubernetes distributions from the cloud provider. But it allows us to select a specific HPC tailored OS. The challenge on AKS is that they constantly update the host OS. So even if you compile things for a specific kernel, they're outdated after a week already. So let's conclude with a customer use case, 3DT Holdings project of running simulations for repairing defect heart valves. 3DT Holdings' challenge was to run a huge amount of real heart simulations to train a machine learning model for faster prediction. So millions of people suffer from heart valve disorder. 3DT Holdings is building a decision support solution for surgeons for real-time guidance in their operation room. For that, machine learning models needs to be trained with a great amount of accurate simulations. One simulation run typically takes between 6 hours and 3 days on the best performing cloud machines or workstations. But they had a very tight budget of $20,000 and an agile working model, so simulations have to run in batches over a period of many months. The initial or a standard setup brought up many questions. So first, UberCloud's engineering simulation platform with one click created a 50-node GKE cluster with the latest C2 instances, running UberCloud HPC containers with Abacus simulation software and an internal HPC workload manager attached to a shared storage Google File Store. But when using preemptible instances, that would cause too many broken simulations, because at that time, Google had this 24-hour limit of running instances. We also predicted that there would be so many wasted, unused resources, as when the cluster is running out of simulations, a lot of unused hosts were around. So overall, this solution would have been too expensive. So we quickly moved to our second iteration, where our platform created a single-node cloud-based desktop running Abacus. This is used for the engineer to upload simulation files, download results, doing pre-processing and post-processing through Abacus desktop. This desktop was running in a single node GKE cluster connected to Google File Store. Then the engineer uploaded his simulations in batches in different directories. UberCloud simulation platform picked them up and created for each simulation a GKE cluster with just one node, running one simulation, in average about 6 to 8 hours. We had up to 30 simulations running in parallel, which means we had up to 30 GKE clusters running in parallel. On the UberCloud side, we had a SUSE Rancher installation on Azure, and as well as the Abacus license server, which the cloud-based desktop needed to access, as well as the simulation jobs. As key results, we can say that we run 3,000 simulations within the given budget, from which 1,000 was used to train the model. It was running in batches, up to 30 GK clusters in parallel, due to the license limits. The GK cluster creation, simulation run, and destruction and throttling of the workload was managed by an HPC workload manager inside UberCloud's platform. The preemption, which happened at maximum after 24 hours, this never happened or happened very, very rarely. So we had to re-execute or rerun simulations not very often. Google File Store had to be increased multiple times since the simulation output files has been large. So storage became, at the end, a huge factor. So we moved the data to more cheaper cloud buckets as a long-term storage, and also for downloading the simulation results later on. UberCloud benefited from the Rancher integration by having an easy monitoring tool, so we can see in Rancher one cluster as one simulation. We could look at CPU usage. So if the CPU usage was not 100%, there must be something wrong. So we looked into the cluster. We also tracked memory usage and found some situations where licenses was not picked up, or since the license expired after a couple of months, and things like that. So all that we did from Azure without looking into the Google account. So thank you everybody who was involved in this project, especially Jakub, who is the engineer running the simulations, Ender and Wolfgang from UberCloud side, and so many people from SUSE, Google, Microsoft. We all got a joint HPC Editor's Choice Award for the best use case of HPC in the cloud 2021 for that. Thank you, everybody, and goodbye.